Hello everyone, my name is Hemasai Ishwar Reddy Jambula and today I will be presenting the paper Community Detection in Directed Weighted Networks using Voronoi partitioning published in Scientific Reports. This work introduces a new community detection method that works especially well on networks where edges have both direction and weight, which many traditional algorithms cannot handle properly. In this presentation, I will start with the motivation behind the work, then move into background concepts. After that, I will explain the methodology of the Voronoi-based model, followed by results from several real datasets. And also, in the next, I will cover the critical reflections, including strengths, limitations, and key findings, and finally, end with key takeaways and the conclusion. Let's move on to the introduction and motivation. So here I'm explaining about the introduction and motivation. Real world networks like brain connectivity, airline routes, and social interactions often contain both direction and weight. Direction tells us the flow of information or influence, and the weight tells us the strength or probability of the interaction like which is made. Most traditional community detection methods simplify these networks to undirected or unweighted versions, which removes important structure and leads to less meaningful results. So, the dense graphs, such as like brain networks, where almost every region connects to many others, pose an even bigger challenge because typical algorithms fail to separate meaningful groups. This motives the need for a method that naturally incorporates direction, weight, and structure without oversimplifying the data. The paper addresses this gap by proposing a Voronoi-based approach tailored for directed weighted networks. So now moving to the background, like concepts and prior work. Community detection aims to find tightly connected groups of nodes. Algorithms like Luvian, Leiden, and Infomap and SBM are commonly used, but many of them assume undirected or unweighted networks. This assumption doesn't hold for many real datasets. The idea of Voronoi diagrams dividing space based on distance is adapted here to divide graphs into meaningful community regions. Now move on to the limitations of existing methods. Most existing algorithms cannot incorporate both direction and weight at the same time. Many require manual transformations of weights, which causes loss of structural information. They also struggle with dense networks like brain graphs because everything seems connected. Some methods are unstable or produce trivial communities. So, like these limitations motivated the need for a better approach. So, in this, we are discussing about the proposed Voronoi based model. This diagram visualizes how the Voronoi regions work on graphs. The central black node acts as a generator, and the dotted boundary shows the parameter or determines the size of its region. Each node is assigned based on the shortest directed path to a generator, and also you can notice that how the arrows show direction. Like this is something previous methods cannot use effectively. Also, we can see that the weights influence the path length. So even if a node is close, a low weight can make the path less favorable. This visual helps us understand why this method preserves much more structural information. So now moving on to the key definitions and formulas. The model uses several mathematical components. Edge length is computed using a transformation of the weight combined with an edge clustering measure. Local density identifies potential generator nodes. Directed modularity is used to evaluate the quality of the partitions. So, like these formulas help combine both weights and topology into the meaningful distances. Now, let's see the how the algorithm workflow works. This flow visually describes each step of the algorithm. As you can see in the diagram, starting from weight transformation, the graph is converted into a set of lengths. Then using these lengths, Dijkstra's algorithm computes paths to generators. The generator selection step is a crucial. Only nodes with locally high density become generators. This ensures that we start partitioning from important or central nodes rather than the random points. So finally, the R parameter acts like a zoom level. A larger or leads to fewer larger communities, while a smaller or finds more fine-grained communities. This visual walkthrough makes the algorithm very easy to understand. So now we can like get into the results. First, we can go through the structural brain network analysis. The first real-world dataset used in the paper is the structural brain network of macaque monkeys and mice. These networks are very dense, which makes community detection difficult for many traditional algorithms. In these datasets, edge weights represents the probability of information flow between brain regions. Like in this, the authors apply a negative log transformation so that stronger connections become shorter distances, like making the graph more meaningful for the Voronoi model. Like by using this approach, the method identifies five clear clusters in the McQueen brain and four in the mouse brain. These clusters align with known functional areas, like such as visual, sensory, and association regions. Overall, the results shows that the method can detect meaningful structure even in dense and complex biological networks. So this is a like great breakthrough that the authors like they used to represent. Move into the results of the social network analysis. The method was also tested on two social networks, a high school friendship dataset and a university residence hall network. In these networks, relationships are often directed and weighted. Like, for example, if a person may nominate someone as a friend, even if it's not mutual, traditional algorithms usually ignore the direction. Using the Voronoi based approach, the algorithm was able to detect clear and realistic social groups, like students who interacted more closely or belonged to the same circles naturally formed communities. The weighted transformation of 1 by W helped represent strong friendships as shorter distances, which improved the clustering. Overall, this method works well and produced meaningful social communities even without simplifying the direction of the weight. Like as you can see, 1958 Illinois Friendship Network and Australian Residence Hall Network, like these two are they used like in this after using the algorithm, it identifies the natural friends groups. Let's move into the geographical network analysis. This image shows the final community structure detected in the McPhee brain network using the Voronoi Bayesian method. Each color represents a distinct functional cluster formed by grouping brain regions with strong directed and unweighted connections. So, what's important is that this brain network is extremely dense, which usually makes computation detection very difficult. However, the Voronoi method still identifies many clusters that match known anatomical divisions. You can see that visual areas, sensory areas, and frontal association regions each from their own clear clusters. So, from this demonstrates that the method is capable of producing biologically interpretable communities even in very complex and high density networks. So here, as you can see, the Australian migration networks forms communities that closely match geographic regions. So you can see that in image and you can go through that. Large airports naturally appear as generator nodes because of their higher connectivity. Let's move into the benchmark comparisons. These plots compare the Voronoi model with Infomap, Leiden, Luvian, and SBM on synthetic benchmark networks. The x-axis shows the missing U values, which means measures how hard the network is to detect communities in. Higher U means the communities that are blended and difficult. As you can see in the diagram, notice that the Voronoi curve decreases smoothly, meaning its performance degrades gradually rather than collapsing suddenly. So from this, like this indicates stability. Like it's an important property for real world data. Also, in many regions, the modularity achieved is comparable to or better than the Leiden and Luwian. Like as you can see, the like this chart strongly supports the idea that the method is competitive with state-of-the-art algorithms. So by moving to the robustness of generator selection, like as you can see in the diagram, these plots show how stable the algorithm is when generator nodes are perturbed. Like the blue bars represent the case when generators are randomized within their own communities. There is almost like, as you can see, there is almost no change in mutual information or modularity. The results remain tightly clustered near the baseline, like near the baseline value. And the orange bar represent completely random generator placements. So here the drop in the quality is dramatic. Like this constant this contrast shows the density based generator selection, like it's crucial and effective. And also it confirms that the method doesn't depend on arbitrary random choices, which is a major strength. So now move on to the critical reflection. Like you can see the key findings. So these are the like five key findings which I found in the paper. The method effectively handles directed and weighted networks without losing information. And also it produces interpretable communities across brain, social, and geographic data. Its results remain consistent under perturbations. Benchmark performance is competitive or better than several well-known methods. Overall, the method creates a unified and flexible approach to community detection. So the method provides a unified geometrical topological framework, making it adaptable to many real-world network types. And also the benchmark test shows competitive performance matching or exceeding Luvian and outperforming Infomap in stability. Now we'll discuss about the strengths and limitations. One of the main strengths of this method is that it naturally incorporates both direction and weight, something most community detection algorithms still struggle with. Instead of converting the network into an unedited or simple version, the Voronoi based approach keeps the original structure intact, which means we lose less information and get more meaningful communities. Another important strength is flexibility. The model allows different weight transformations depending on type of data. For example, in brain networks, we can use the negative log of the weight, while in social networks, we can use an inverse weight function. This adaptability makes the method applicable across many different domains. The method is also stable. The generator selection process based on local density ensures that small variations in the graph do not drastically change the output. The robustness tests in the paper clearly showed that randomized generators only within communities barely affects the results. Like when we see the limitations, one challenge is that the quality of the results depends on choosing a suitable weight transformation. If the transformation is not appropriate for the data set, the algorithm may not represent the network structure correctly. Another limitation is tuning the R parameter. Different data sets may require different ranges to find the optimal community resolution. Finally, while the algorithm is efficient, very large scale graphs may still require more computation compared to simpler methods like Luvian. So now move on to the key takeaways. The real world network requires models that can handle both direction and weight. And this method does like so naturally, it works well across multiple domains, brain mapping, social groups, and also the mobility patterns. The algorithm is stable, flexible, and competitive in accuracy and efficiency. It offers a framework for analyzing complex networks. Now, let's move on to the conclusion. To conclude, the Voronoi based method provides a strong practical solution for detecting communities in directed and weighted networks, which many traditional algorithms struggle to handle. By adapting Voronoi concepts to graphs, the method preserves important structural information instead of simplifying the data. Across different experiments, including brain networks, social interactions, and geographic mobility, the method consistently produced meaningful and interpretable communities. It also performed competitively with well-known algorithms like Luvian and Leiden, while showing better stability than Infomap. Overall, this approach is flexible, robust, and effective across many types of real-world networks, making it valuable tool for analyzing complex systems where direction and weight really matter. Thank you for listening.